Hey guys, today we're going to take a look at section 9.4. We're going to talk about what are called geometric vectors. Well, we're going to talk about vectors, and today we're going to look at these vectors geometrically, kind of get an idea of what we're talking about visually, and in the next class we'll kind of take the visuals away and we'll talk about these things more algebraically. So first off, what is a vector? A vector is a quantity that has both magnitude and direction. So magnitude means it has a certain amount of strength behind it, and then direction means it's going, well, in a certain direction. Okay, so examples would be force. Okay, you're pushing against something. Gravity is pulling you down, so there's a direction involved with that. The magnitude of gravity on Earth versus the Moon versus Mars, they're all going to be different, so there's a different magnitude. Wind can blow north, south, east, northeast, whatever, and it could go 20 miles per hour, 40 miles per hour, 5 miles per hour, okay? So those would be examples of magnitude and direction with something like that, okay? Now, it's customary to represent a vector by using an arrow. The length of the arrow, so longer arrow means greater magnitude, and the arrowhead would indicate the direction of the vector. So what you see over here, this is an example of what's called a directed line segment. So it's a line segment. It begins and ends. But that arrow right there is showing you the direction of it. So this isn't a line. It's not a line that's going infinitely in one direction. It starts and stops, and the arrow is showing you what direction it's like going. So it's starting here and it's going in this direction. Okay, we could call this vector, this could be vector A. We could also call it PQ. Again, P being the initial point and Q being the point that it's headed towards. And then the magnitude we could write this way. Again, you'll notice this looks like the absolute value notation. Okay, now two vectors are equal if they have the same magnitude and the same direction. So both of these things have to be true. So look at these examples over here. Consider the 6 vectors which are equal. So which of those vectors would be absolutely equal to each other? Looking at it, I would say Z and W. Oh, sorry, Z and Y. Z and Y would be equal. Maybe U and V look like they're probably equal to each other. Which have the same direction yet are not equal. So X and W are going in the same direction. They're both headed, headed to the right or headed east, but this one has a much larger magnitude than that, so they're not equal to each other. So X and W would be examples. They're going in the same direction, but it's different. They're not equal to each other. And then which have the same magnitude but are not equal? Well, looking at this picture, now we're kind of making if you want to know that they have the same magnitude, we'd probably have to measure them. But for example, it looks like, I think V and W are like the same length, but they're going in different directions. And so that makes them not equal. Okay, so even if they're the same length, they're not going to be equal to each other. So I'm going to say V and W, also W and U, because V and U are equal. So if W is not equal to V, W is also not equal to U. So W and U would be example of vectors. So again, you can't just have the same length and say, oh, this is 3 centimeters and this is 3 centimeters. They also have to be going in the same direction to be considered equal. Okay? All right. We are going to look at adding vectors. We're going to add, we're going to subtract, and we're going to do a little bit of multiplying with things today. So first off, adding vectors geometrically. I have 2 vectors here. This is vector V and this is vector W. And this vector right here is the result of adding V and W together. That has a special name. It's called the resultant. Okay, and it's just what you get when you add these 2 vectors together. There's 2 different ways to add vectors. I like to add them by using this, it's called the tip to tail method, where this is vector V. Vector V is going in this direction. It starts here and stops here. And then where vector v stops, that's where we start drawing vector w. So vector w starts here and stops here. My initial starting point and my terminal, like ending point, the connection between those, that's the sum of these two vectors. So think of it as there's a force pushing you this way. There's also another force pushing you this way. So the result is, where did I start and where did I eventually end up? That would have been a force going along that path. Okay, so that's geometrically how to add vectors together. Now, before we can talk about subtracting vectors, we have to talk about what the opposite of a vector is. So if v is a vector, negative v is the vector having the same magnitude but traveling in the opposite direction. Okay, so this is vector v, this is vector negative v. Do not, this is, and I'll explain this later again, don't think of this as slope. Okay, this is the opposite of the vector. If this vector is going up and to the right, the opposite of that will be going down and to the left. Don't think of it as like positive slope and negative slope, and they're traveling along the same line. It's just that the arrowhead is on the opposite end. Okay, so this is the positive vector. The negative vector just takes that arrow and moves it to this side. Okay, and the reason we need to know that is because that's how we're going to subtract vectors. So to subtract something geometrically, we're really going to add the opposite of that vector, and that's what subtraction will be. Now, the last thing we can talk about is multiplying a vector by what's called a scalar. So we're not taking a vector times a vector. Okay, we're going to take a vector and we're going to multiply it by a scalar. A scalar is just, it's a quantity with only magnitude. So there's no direction to it. There's just magnitude. So examples of scalars would be mass, length, time. There's no direction to time. I guess you could say that time's always moving forward, but it doesn't move north. That doesn't make sense. Temperature. Okay, so you can measure the temperature of something, but there's no direction involved with that. Geometrically, when you multiply a vector by a scalar, it's just multiplying. So this is an example of vector. This is vector v, and this is vector 2v. So we're multiplying this vector by a scalar. The scalar is 2, and all that does is it doubles the length of the vector. Okay, this would be an example of multiplying a vector by -1. Again, all it does is reverses the course of the vector. Instead of going up and to the right, it goes down and to the left. So you can literally think of this as 2 v's. Okay, 2v is equal to 2 vector v's laid tip or end to tip, tip to tail is what they say. This is the tip, and then there's the tail of it. So that's an example of multiplying by a scalar. Okay, and the reason you're going to need to know that is to add these vectors that I have on the bottom. So this is where we're going to stop. This is actually the beginning of the next day's notes. So how do I add? So here's my vectors. I've got vector v. Notice vector v is going 1, 2, 3 to the right and up 2. Then I've got vector w here. Vector w is going down and to the right, so it's going like down 2, and then it goes over 2. And then I've got this vector u here that goes like over 1 and up 1, 2, 3. And what I want to do is I want to know the resultant. Okay, what do I get when I add 2 v's and then I subtract the w? All right, so this is just a grid. There's no numbers, there's no XY axis. It's just a grid for us to be able to draw this. So like I'm supposed to draw 2 v's, so I'm going to draw a v and then another v. So this is going to be going up and to the right. And then I'm going to subtract a w. Well, w goes down and to the right, so subtracting w will go up and to the left. It'll be the same line, but the arrowhead will be on the other side. So all in all, I'm going to go up and then I'm going to go this way. So I'm going to start my graph down here, just anywhere down here. And then I'm going to do 2 v's. So 1, 2, 3, 1, 2. 1, 2, 1, 2, 3, 1, 2. There's a v. 1, 2, 3, 1, 2. There's another v. And then I'm going to draw W, but I'm going to go left 2 and then up 2. Left 2 and then up 2. Because I'm drawing negative W. Now, this is not my answer. My answer is the vector that starts where I started and ends where I ended. And I just broke my pencil. Ends where I ended. And that is this is the result, which is vector 2v minus w. That's the answer. Okay? All right, let's look at B. B, I'm going to take vector v, and then I'm going to subtract 2w. So again, I'm going to go v, which is up and to the right, and then I'm going to subtract 2 of these. So I'm going to go up and to the left, and then up and to the left again. So I'm going to kind of go from the bottom, and then it's going to end up over this way somewhere. So I'm going to start. I just have to have an idea of where to start so that I don't run off the grid. That's all I'm doing. Okay, so V. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. That's V. And then I need to subtract 2 W's. So I need to go up and to the left. 1, 2. Negative W. And then do that again. 1, 2, 1, 2. So again, this is your answer. Start where I started, finish where I finished, and this is the vector, and I like to write V minus 2W. There, now you can see it. Okay, that's my answer. Do not leave that off. And do not just make a triangle, don't continue, start here, draw an arrow this way, draw an arrow this way, draw an arrow this way, and then draw the arrow back this way. Don't make a loop with your arrows. That's not what we're doing, okay? Start where you started, finish where you finished. Okay, so see if you can do the last one, example C, and come up with your final answer. I'll give you a hint. You probably want to start in this area over here so you don't run off the grid. Okay, just somewhere over here about the middle left of the graph. Okay. All right, so I just drew that. Well, hopefully you were doing the same thing. So this is my final answer. This is my resultant. Okay, it goes from here, goes down and to the right. So I drew a V, then I drew a W. Now remember, this was a positive W. Okay, so over here I was doing negative W, so they were going up and to the left. This should go down and to the right. Then I should draw another one down and to the right again. Then I drew the opposite of U. U was going up and to the right, so I went in the exact opposite direction, down and to the left, and that's where it ended. So my entire graph started here and ended here, so that is my resultant. Okay? Take a look at the homework and let me know if you have questions on that.